Hi and Assalamualaikum to everyone. So today we are from Group 8 and Section 4. We are going to tell you guys about our design of flash separator in separating between methanol and water. So our group consists of 4 team members, which is the first one is me, Muhammad Ahmad. Second one is Amir Zafar. Third one Sabrina, and also the last one Shalini. So let's go. So let's start with the problem statement. The problem statement is that we need to design a flash column separator to separate a mixture between methanol and water. So based on our research through the internet, we have found that flash vaporization is the best to be used. So before we start with the calculation, we have done some initial assumption to do our calculation. So this assumption is based on the industrial value that we find in the internet. So the initial composition of methanol is that 0.35, and also the initial composition of water is 0.65. The pressure is to be assumed that it is operated in 40 kilopascal, and the temperature is just above the temperature of boiling point methanol, which is 66 degrees Celsius. So we have some other assumption, but we will go to the next slide. So the next assumption is that first one, the basis is set to be 100 kmol per hour. And the second assumption is that the mixture is hence to be in either solution, so Raoult's law can be used to calculate the parameters. And the lastly is efficiency of our flash vaporization is 100%. So next slide are going to tell you guys about the calculation of our pressure, and also the next is X, Y, and B, and also F. Let's go.
Hi, my name is Shalini Nurul, and I'll be presenting the pressure calculation. By using end-to-end equation, saturated pressure of methanol 1 and water 2 can be calculated. By using the end-to-end equation listed in the slide, which is ln saturated pressure equals to coefficient or constant A minus B over temperature plus C, we can get the saturated pressure of methanol 1, which is 106.6198 kPa. Meanwhile for water 2, 26.2422 kPa. Okay, now we will be calculating bulk pressure and also dew pressure to detect whether the given pressure that we assume are suitable for flash calculation or not. So, bulk pressure are calculated with relating the vapor phase composition. So, the equation will be X1 P-set1 for methanol plus X2 P-set2 for water. It will resulting in 54.3744 kPa. Meanwhile, for dew pressure, it will be relating to liquid composition for methanol and water. From the slide, the equation is 1 over Y1 over P-set1 plus Y2 over P-set2. The dew pressure is 35.6481 kPa, since the given pressure or the assumed pressure is 40 kPa and it lies between bulk pressure and dew pressure. The system is into phase and flash calculation is possible.
Assalamualaikum and hi, my name is Sabrina and I will continue with flash calculation. So in flash calculation, we need to calculate moles of liquid L, moles of vapor V, liquid phase mole fraction X1, X2, and lastly vapor phase mole fraction Y1 and Y2. So first of all, we use Raoult's law in order to find the liquid phase mole fraction and the vapor phase mole fraction. By using the Raoult's law equation, X1 times with P saturation equal to Y1 times P, and same goes to X2 times P sat equal to Y2 times P, where we can rearrange the equation and get X1 times P saturation for the first substance plus X2 times P sat for the second substance equal to Y1 plus Y2 times P equal to P. So, since we already calculated the P saturated for both substances in the previous slide, we substitute back the value into the Raoult's law equation that we already rearranged and get X1 equal to 0.1712 kmol per kmol. And for X2, can just be calculated using 1 minus X1 and get 0.8288 kmol H2O per kmol. Next, for vapor phase mole fraction Y1 and Y2, first to find Y1, we use Y1 equal to X1 times P saturated for the first substance, divide by P. So substitute X1 and P saturated that we already calculated previously inside the equation, and we get Y1 equal to 0.4563 kmol methanol per kmol. And for Y2, we calculate using 1 minus Y1 and equal to 0.5437 kmol H2O per kmol. Next, in order to find mole of liquid L and mole of vapor V, we use equation Z1F equal to X1L plus Y1V, where Z1 is the initial mole fraction of methanol and F is the free molar flow rate. So we substitute all the known value inside the equation that we calculated previously and get mole of liquid L equal to 0.3729 kmol per hour. And lastly, to find the mole of vapor V, 1 minus L, which is 1 minus 0.3729, and we get 0.6271 kmol per hour.
Hi, I am Ami Asfar. So this is our XY diagram. Actually, the XY diagram is a graphical representation used in distillation process to analyze the composition of the liquid and vapor phases within a distillation column. So in the XY diagram, the x-axis represents the mole fraction of one component in the liquid phase, while the y-axis represents the mole fraction of the same component in the vapor phases. In this diagram, the blue line curve represents the vapor-liquid equilibrium curve, where it provides the overall representation of the phase behavior in a binary system at certain temperature and pressure, showing the conditions under which the liquid and vapor coexist. It also indicates the boiling point, critical point, and the overall shape of the phase boundary. So this is our flash column and the overall value calculated from the previous part. The temperature set for our flash is 66 degrees Celsius and the pressure set is 40 kilopascal. The total flow rate entered the flash column is 100 kmol per hour, consists of 0.35 kmol of methanol and 0.65 kmol of water. For the product, the upper stream, which is the vapor stream, the total flow rate calculated is 62.67 kmol per hour, consists of 0.4563 kmol of methanol and 0.5437 kmol of water. For the bottom stream, which is the vapor stream, the total flow rate calculated is 37.29 kmol per hour with a composition of methanol 0.1712 kmol and 0.8288 kmol composition of water.